And usually we talk about these in terms of gases or in terms of solutions. Solutions are the ones that ideally fit this one. So we have two examples of reactions. This is one that's been on the AP test, and then there's another one that shows up on the AP test a lot. So SO2 plus oxygen, both of these are gases. And a double arrow here, because we're talking about reversible reactions, and we have 2 SO3. So it's the production of sulfur trioxide. So there are a couple of examples here, and then you guys, while you're studying, you can take a minute and color these things in, because you know they've got pretty pictures on here and so on. Okay, you guys caught up with me? Yes? You can use the same color throughout. It doesn't matter, but just as long as you're using color of some kind, it tends to show up better. Do you need some color?
No, we do it.
Okay. All right, so flip the page. And what we have on here is equilibrium again. And recall again that equilibrium is dynamic. It's not a static. Static means it's totally still, totally unmoving. When you say dynamic equilibrium, what you're doing is you're saying, hey, there's a constant rate as the molecules of the products are being converted back to the reactants. That's what dynamic equilibrium is. The forward rate of reaction is the exact same as the back reaction. So the molecules of the reactants are being converted to products at the same rate, not the same amount, it doesn't mean they have this, again, and I'm going to say this over and over again, it doesn't mean everything's the same concentration. It means it gets to a point where you have the same amount of products being produced as reactants being produced. So it's not the same concentration. It means it gets to a point where you've got 5 molecules of product being produced for every 5 molecules of reactants being forth like that. So the forward rate is going to be equal to the reverse rate. So the molecules of reactants are being converted to products at the same rate as molecules of products are being converted to reactants. Does that make sense to you guys? It's only at equilibrium that this happens. So to start off the reaction, you've got a lot more products being made, right? But it gets to that point where you have a balance. And so the same amount is happening in the forward as the reaction. It could be that it's way over towards the end where it's almost all completely and totally product with just a little bit of the reactants left over. Or it could be a reaction that's hardly nothing's happening. But you've got a little tiny bit of the reactants forming products and the products forming the reactants. It just depends. There's like a continuum where it is. Somewhere along that continuum it's going to stop, and that's where you're going to have equilibrium, where you still have things changing, you still have things reacting, but they're going back and forth so that overall nothing's changing. It's in an equilibrium. The forward and reverse reactions occur at the same rate. So K rate of the reactants equals K rate of the products. This is the rate of reaction, right? But we can't use these numbers to calculate the rate from this. You know, we talked about calculate the rate constant and calculate what exactly is the rate in molarities per second or something like that. We can't use this for rate calculations. Okay, so don't get into that thinking, well, yeah, equilibrium, I can then use this and calculate the rate and blah, blah, blah. No. You have to have data, actual physical data, lab data to calculate the rate. Always remember that. That's going to be a question on the test. what do you need to calculate this? Or here's your information, can you calculate the rate from this? No, you have to have data. Okay, so I'm going to grab two colors. You need two colors for this graph because we're going to have two lines on the same graph. So down here on the forward reaction, and I'm going to use this equation right here. So let's do H2 plus I2 produces 2HI. So we've got the products and we have the reactants. And if I look at the products, I'm going to use green for the reactants, sorry. So if I look at the reactants, in the forward reaction, I'm going to start off with some amount of hydrogen gas and iodine gas. And you notice they have the same coefficient in front of them, right? So they're molarly, if we have just perfect amounts, the moles are equivalent. So they're going to lose at the same rate, yes? So I'm going to start this off, and I'm going to say, okay, here's my iodine and my hydrogen. Those aren't always the same. Okay, it just depends. It really depends on the coefficients in front of these. It could be if we had a 2 in front of the H2 and a 1 over here, then the hydrogen would be lost twice as fast as the iodine, right? Right? Because for every 2 moles of iodine that we use, we're only using 1 mole. So for every 2 hydrogen we use, we would only use 1 mole of iodine. Yes, I had a 2 in front of there? Okay, so they'll ask you things like that. Not talking about grams or mass, just in terms of moles. So look at that in terms of moles and see what's going on. So here is my iodine, and I'm going to grab another pen, and notice that this has a 2 in front of it. So this appears at twice the rate that this disappears, right? Yes, do you see that? Because for every 1 mole of this that disappears, I get 2 moles of this, don't I? So my line started off with 0, right? My line is going to be a little sharper, and again, I'm not measuring this out, but my line is going to be a little steeper, right? Because the rate of this is twice the rate of this. Yes or no? Okay, so here is my HI gas. I don't know why I put gas, I just felt the need of it. Okay. If I do the reverse reaction doesn't have to be exactly the same as this. It doesn't have to be just the opposite of this. It depends on, remember, the reverse reaction doesn't have the same endothermic, like delta H. It doesn't have the same delta H's and stuff as the forward reaction. So it's not just a copy of this in reverse. It's not the exact same as what's going on here. So the reverse reaction for this one would be that, okay, so I'm starting off with a high amount of HI, right? And so I'm going to lose some of that. And here's my HI gas, right? I'm starting out with a very low amount, not 0. I'm starting out with a very low amount of the H2 and the I2. And it's going to go up, but it's going to, again, reach that balance. Looking at these two reactions, which one is more thermodynamically favorable? The forward reaction or the reverse reaction? The forward reaction, right? Because look at this one, the reverse reaction, we start off really high and we lose a little bit going reverse reaction. We start off really low and we gain a little bit at the H2, but it's not much going on, is there? It's the forward reaction that happens. So what we would say for this reaction is that when it's at equilibrium, it's shifted to the right. It's shifted to the right. So it's right shifted. It's typically thermodynamically favorable going this way, just by looking at the graphs. Yes? We can't get any numbers associated with it because the graphs have no numbers on them. But by looking at the graph, we can look at it and say, yeah, this is a right shifted thing here. Yes? So when it attains equilibrium, it's going to be mostly products. There'll be some reactants in there, but the vast majority of them will be products. Yes? Okay. And I did not have my, I didn't have my thing plugged in here. Okay, now you can hear me. Blah, blah, blah. That's all you heard. Write that crap down. Should have been in class. Okay, so down here on the next part down here, the equilibrium requires a closed system here. Okay, a closed system. Closed system because you can't let things escape. If you open the system, you no longer have an equilibrium. It will continue on until everything's gone. So if I have my Dr. Pepper and I shake it up and I take the lid off, it's ultimately going to go completely flat, isn't it? I have let all the gases escape until the pressure inside the bottle equals the pressure outside. If I shake it up and maybe take the lid off a little bit and let it go, or if I just shake it up and leave the lid on, it's going to create a new equilibrium, right? Because it's a closed system in there. If I shake it up and let a little gas out and then close it back up, I've changed the amount of carbon dioxide in there, right? And so what happens is I've messed with the reactants. So I've altered the amount of stuff in there, but it's a closed system again, and I can see what happens from that. So equilibrium requires a closed system, so no reactants or products can escape. The open system always allows for escape of gases, not the liquid. If you're doing solutions, where you've got two solutions and you're just mixing the solutions together, that's not a problem, because the liquid's not going to jump up out of the beaker. But if you're dealing with gases, if there's a gas of any kind produced, then you have to worry about it. So this is just because open systems allow for gas escape. Reactions in solutions are the best. Reactions in solution, it's a naturally closed system. So when you have these reactions in solution, it's not a problem. You don't have to have a lid on it or anything. As long as you make sure that you're not letting stuff leak out, then you're fine. It's the gaseous ones that any type of gas, if you put two solutions together and a gas is formed, then you're going to have to make sure that the system is closed in that. And it's tough when you're dealing with gases to have a closed system. Do you remember vaguely last year where you had to prove the law of in pre-AP chemistry where you had to prove the law of conservation of mass with a glove, and you put the stuff in the fingers of the glove and you poured it on there? Yes? Vaguely you remember that? You didn't do that one in yours?
I don't remember.
You had to figure out that you had to duct tape everything on, and when you put it on the scales, didn't it change just a little bit?
I think I remember that.
Yeah, do you guys? I had some people that were freaked out because it was like, no, it disproved the law of conservation of mass. It's like, no, honey, you used a rubber glove from Walmart and duct tape. So the system, when we closed the system, it wasn't a perfect setup, because when you talk about gases and you're using a closed system, you really have to work hard at it to make sure it's a closed system. Yeah. So when we talk about proving the law of conservation of mass, if it's all in solution, yeah, it's pretty easy to do that. But when you deal with gases, it's tough to make that system a closed system. Okay, next page. Okay, so Le Chatelier's principle. When we talked about this in pre-AP chemistry, basically I gave you a really simple, straightforward definition. Le Chatelier says that when you have a system, and when we're talking about a system, we're talking about a chemical reaction, if you put the system under stress, you stress it somehow, change the temperature, shake it up, do something like that, it will create a new equilibrium. So it's balanced out, it's settled, it's nice and neat. You mess with it, it will change things up, and then it'll create a new equilibrium. That's what Le Chatelier's principle says. Now we can be a little bit more specific with the Le Chatelier's principle. If one or more factors that affect equilibrium, here we go, let's put this down. Is it affect or effect on that one? Affect? Yeah, I have to stop and think about it. Okay, EQ is equilibrium. Okay, so if one or more factors that affect equilibrium is changed, the position of the equilibrium shift, so let me say this again, the position of equilibrium shifts, it changes in the direction that opposes the change. Hang on just a second and let's do this really quickly. So if I have that H2 plus I2 produces 2HI, right? If I have this, what they're saying is if I add more iodine gas, okay, that's obviously going to have an impact. If I add more here, then it's going to shift the equilibrium to deal with that stress, that change that I put on it. And what that means is it'll shift away from that. Because if I add more reactant, isn't more product going to be made? Then it's going to shift so where there's more product. So when it says shift, again, think of it kind of like a continuum. And here is where our thing is. Here are the reactants. Here are the products. So let's say that it was balanced here. Here's the equilibrium. And then I messed with something like I added I2, then the equilibrium is going to shift. So maybe now the new equilibrium is here. If I take some of the hydrogen iodide gas out, right? I take some of this out, isn't it going to shift more this way also? If I add more of this in, if I add more of the product in, it's going to shift it away from that, so we'll have more reactants made. So I can mess with the amounts of stuff in here. That's a way of stressing it. I can mess with the temperature. I can mess with the pressure. And that's going to cause where the equilibrium is, like the equilibrium is how much reactant, how much product, right? It can shift where that is. So the amounts of things will change and it'll become a new equilibrium. Yes? Okay, pause right there and go take a break.